everyone. So our today's speaker is Dr. Hailin. Dr. Hailin is a professor in electrical engineering at the University of Notre Dame, where he got his PhD degree in 2005. So between 2006 and 2011, Dr. Hailin was assistant professor at the National University of Singapore. And his research is at the intersection of theory, AI, robotics, and formal methods. And the applications of his research includes cyber physical systems, human-robot collaboration, multi-robot operation tasking, and also safe AI. So Dr. Hailin has served as the chair for IEEE CSS Technical Committee on District Event Systems for multiple years, and he was the program chair for many conferences over the last few years. And he's a senior member of IEEE and the recipient of the 2013 NSF Career Award. So today, Dr. Hailin will give us a fantastic seminar about towards scalable autonomy.
Thank you. Thank you for introduction, and thank you for invitation, and thank you for your time coming here. I hope I can make it interesting. So I'm from Notre Dame. This is main building of Notre Dame. You got a chance. It's just 2-hour driving, and we play football every year almost, right? So I'm a football fan. That's the reason why I come back. So we talk about scalable autonomy because that's my main interest. I think I background is control. I work on formal methods, but control, you know, is more physical system. Formal methods is very high level, computer science, logic stuff, and so on. But I found there's a bigger gap. Yeah, there's a big gap about the formal methods and the physical system. Recently, I just try to fill the gap. I mean, my knowledge actually is not there. So I found a perception, vision, and so in principle, I think my whole research can be under this big umbrella autonomy. Definitely is today we are share scalability because there's two major, in my opinion, there's two major challenge. One is the scalability, and another is uncertainty. So we are mainly talk about the scalability, and what we really talk about is actually three phases. One is scalability due to the task planning. In the sense is if you have very complex tasks, not just motion planning, point A to point B or integration. If you have a lot of things or tasks you have to achieve, so that's a more formal methods approach, and that is complex. And how we deal with this kind of complexity. Another is leg locomotion. That's mainly due to the complexity due to high degree of freedom. Yeah. So so how can we be able to scale it up? That's the main question, right? So we have high dimension systems. How we do that? And the last question is manipulation. Is this complexity mainly due to you have a very complicated contact pattern? When you make contact, break contact, this is actually hybrid system. You have quite different modes. So some autonomous, some controlled. So how we deal with this? All they are, if you are in robotics, you understand they are not trivial problems. But if you not in robotics, you say, oh, that's simple problem. So let's see. And also today's talk is mainly based on my PhD student, recent graduate, Vince First. He's very good student. That's basically his work. Yeah. So I just kind of present his work. So all the credit goes to my students. All the mistakes is mine. Okay, so why is difficult? And let's start with something everybody agrees is needed intelligence difficult. It's playing chess. Why is difficult? Because again, it's scalable, right? So it's need a lot of intelligence to play it, and this estimation is 10 to the power 120. That's even more than all the atoms in the universe. It's very large scale. So this means many searching problems. What's the best move? So that's many searching problems. But this problem basically is solved. In the sense is, this is later 90, and the IBM have this supercomputer, Deep Blue, that will be able to beat the human champion. Nowadays, just pick up cell phone, get app, and you pretty much you can beat the human chess player. So this problem eventually actually solved. But if you look at it in the picture, there's still a human there. And IBM spent $1 million to develop this supercomputer, but why they just forget one small thing, so to move the pieces. So we argue is actually this is because it's not really trivial. And you say, oh, what's a big problem? So that's 97, right? So nowadays we have AI, robotics, and we already make a lot of achievements, and it's still difficult. Yeah, actually, not long ago, this happens actually with accident, robot arm, accident grab the boy's finger and broke it. And that's there's definitely blame is the boy actually moved too fast. Yeah, not supposed to move, not supposed to reach the robot arm leave and then move to the piece. But the boy cannot reach, and so that's why it was accident. But anyway, still, it's not safe. Yeah. So this simple grab and place is still difficult in the senses we are not 100% sure. So still not really solve the problems. And you can argue, okay, oh, then why just let the human do what humans do that, let the computer do what the computer is doing? Why not? We just do that. Well, there are certain cases that we need really autonomous robots be able to achieve although these simple tasks. This is the tsunami Fukushima, that's 2011, I remember, because that's the year I fly from Singapore to Notre Dame for interview. So due to this, I need to change my flight. I supposed to connect in Tokyo, but they nicely changed in Hong Kong. So I remember exactly what happened. Actually, that's a case I want to bring up because after this meltdown nuclear plant, then there's a lot more need to be cleaned up. So to close certain valves and so on. So it's a very dangerous job. It's high radiation. And it's a sad story, but a very touching story because the retirees, they volunteer themselves to do this cleanup. And the only reason is because if you come to the metal nuclear plant, your rest of life maybe just weeks. Yeah, so that's very sad. But they go there, they don't really need that real trained skills. They just go there and turn off and avoid collision and so on. So it's not really need a very high skill trained engineer to do this job. It would be nice if we have some robots would be able to do that autonomously. So that save lives. So that's kind of the main reason motivate my research. Mainly focus on is solving this autonomy problem, not really solving, just push, right? So push this. And why it's difficult? And we are going to talk about one branch, which we believe that's the main difficulty that we still lack fundamental approach to effectively handle, which is scalability issue. Right? So another thing we don't have time to talk, but I have a lot of interest is how to handle uncertainty. Yeah, hopefully next time I come to Purdue, I can talk about uncertainty. But today we mainly focus on, right? We already mentioned we're going to talk about these three pieces. So temporal logic, task planning. Temporal logic used to be my favorite topic, actually. So temporal logic is one way that you can describe complex tasks for robots. For example, imagine you have manufacturing, construction, not just autonomous driving, motion planning problems. You have a lot of logics. You have certain rules you have to follow. And a temporal logic is an effective way, have very rich, you can describe this specification in a very formal way. And this basically building upon Boolean logic. Everybody familiar, 0, 1, Boolean logic is conjunction, disjunction, negation. And the temporal logic is added some temporal. So you can argue with respect to trajectory. You can argue with respect to a dynamical system, right? You can talk about next state. You can talk about the trajectory, and at a certain point, something have to happen. Yeah, and you can argue if something never happened. You can argue something eventually happen. You can argue if something will happen until certain thing happen, right? So that's kind of the logic. Yeah, so this one definitely have a bunch of literature, actually is a domain, yeah. So how to do it, model checking, and synthesis problem, and so on. So for example, for robotics, we can describe some very simple tasks. So this, for example, you can imagine is configuration space, right? So you can represent robots as a point. So then we can argue is in the configuration space, we have some collision free, we want to eventually reach the target configuration. Given us the region and the green, so we can eventually reach the goal. You can avoid a certain collision, right? And we can say, okay, this could be, you can add one of the blue and eventually go to green, yeah, type of this. So you can build upon this and you can describe the formal description of the tasks. And as the formula become larger and larger, you become more and more complex tasks, and that's generated with scalability problems. The reason why, if you can imagine, the possibility for you to find the trajectory for us is in the configuration space, we found the trajectory to satisfy specification. And there's two types of scalability, right? One is a dimension of the configuration. Another is about the complexity of the temporal logic itself. If the logic formula is long, that usually means a larger searching space. Okay, so there's a bunch of research behind it. And what we are interested in definitely is we try to find a trajectory in the configuration space that we would be able to achieve the tasks. Right? That's a task. That's pretty much. You can think about it is a motion planning process. And there's many ways, and there's one standard, almost standard way in the temporal logic, which particularly with respect to the continuous trajectory, we call single temporal logic. And we can do, usually people do in a way is just discretize using sample data. And we discretize into some dots as we show here. And for each time, you introduce integer variable, 0 or 1. Yeah. And for every time you have this, and every subformula, you have integer variable. And this is how we do that, basically. If you use a conjunction, you have each subformula, you have integer variable. Each one is returning integer variable. And they have satisfied certain constraints. Then that's where imply conjunction. And this is typo, it should be disjunction. So you can build upon this. So the main idea is you break down into very simple Boolean variable. And every time you introduce is a bunch of equations, right? A bunch of constraints that will imply the logics. And you put them together, you can imagine there's a lot of integer variables, a lot of constraints. And for you is to satisfy all the constraints, right? Satisfy all these constraints, and then that's corresponding to a mixed integer problem. So that's illustration of this integer programming. So it's nice, but the problem is this is difficult in the sense is this grow the number of the integer variable introduced every time step you need to introduce. Yeah. So this complexity grow exponentially with respect to the number of the variables. So everybody knows, right? So mixed integer programming is not easy to solve. And that's the complexity problems. That's the scalability. Actually, you show here is the horizon, the time horizon, and the integer variable introduced, and it is explode. Yeah. So that's not scalable. Not scalable. Yeah. So we are going to try to address this. And okay, so another issue is the following. So one way you can reduce, right? So you're just using more larger time interval, so you have less data. So that can help, but that's usually cause the problems. For example, this problem, very simple problems. You have robots. Yeah. So for example, you need to reach region 1, region 2, green. Let's say, okay, you need to pick up the key, and you need to pass the door 1, door 2, eventually reach the goal. Right? Okay. So that's pretty much very simple tasks. You can write it into temporal logic and solving mixed integer programming. And this is a solution given. And the computer solve the problem. But what's the problem? The problem is, well, everything is okay. It's pick up two keys, and then, but it's not, instead of passing the door, it penetrated the wall. And for the computer, nothing wrong. Why? Because you do the sample. If you look, if you can see, there's two blue dots corresponding to the sample data, sample points. And these two integer variables you pick, they totally satisfy the specification. There's no penetration of the wall. But really, if you really implement it, you need to complete trajectory, and you need to penetrate the wall, which is not feasible. So that's the problem. So to avoid this, you need to reduce, or you need to find a resolution of your sample data trajectory. But that gives you explosion problem, right? So that's become difficult, right? So because if you introduce and you have to handle, or you cannot really plan long time horizon. Yeah. So then that's come to some or recent work, how to solve these problems. And what we intuition is, we don't believe these time steps and the number of this the sample is a fundamental bottleneck over scalability. Yeah, so that's all hypothesis. And we think it's just because due to you artificially do this sample data, to do this discretization, that's caused the problem. So we believe we can remove this bottleneck. And yeah, there's a bunch of ideas. So today we are going to talk about my student like 5 years work. So there's a lot of work. So that's why we mainly focus on the high level intuition and idea. So if you're interested in the work, most of the work are published, right? So you can just go and take a look. Okay, so idea is following. So what we do is we borrow ideas from the most recent developments in the shortest path on graph of convex sets. And the idea is combine some ideas from formal methods. And the idea is following. So we can construct a graph. So we construct one thing is we given the logic specification. We can construct a graph which is automata, fine automata. If you're familiar with fine automata, this is what a fine automata looks like. If you're not familiar, it's pretty much the state transition system. You have discrete state, and there are certain states. If you reach that's called a terminal state, and you satisfy the specification. So given logic formula, like we call safe LTL, but it doesn't matter. It's given a logic formula, you will be able to construct such automata. They are equivalent. Yeah, they are more like a graphical representation of logic. So you can always do that. That's from formal methods. Another thing is you can, from the graph, this is configuration, you do the partition, and you have labels, because you have, depends on continuous trajectory. Whether certain property satisfy or not depends on where you are. So based on this, we do the partition of the configuration space. That's where this partition comes from. Well, this definitely could have some overlap. You don't have to really partition a whole configuration space. You can over-exploit the obstacle, right, using polygon and so on. So, okay, but this we can, based on their connectivity, based on their overlapping or not, we can build a graph as well, right? So that's adjacent graph, basically. So then we do the product. We do the product. And the reason why we do the product is when we do the product, we kind of get a hybrid automata and the graph of the configuration space. So we have geometry, we have logic, and we can combine them together. And once we combine together, good thing is, then, okay, when I find a path on this constructed graph, we call product automata, then it satisfies specification. So that's convert this problem into just the search problems. Okay, so that's first we do. But you think, okay, then the graph search problem, but why you need this convex set? Well, the idea is following. So we want to construct a continuous trajectory. So what we do is we convert this into the mixed integer programming. Okay, so wait a minute. You say mixed integer programming. Now you're using mixed integer programming again. But here is the difference is we're going to introduce the constraints. This constraints is due to the sets, due to these convex sets. And each set we introduce a variable we call control points. And based on the control points, we can construct a certain curve, like a Basel curve, for example. That's well understood in the motion planning literature. So the continuity and the convexity and all this differentiability, all we can guarantee actually, right? So basically, by placing the control points, we can get smooth enough continuous trajectory. So instead of do the sampling, then we just pick control points. And the control points become variable. And we pick control points from different regions. This will satisfy certain constraint. This is where this constraint comes from. And we can minimize the total length of this curve. Yeah, so that's kind of minimum path, right? Minimum length curve. And where the integer constraint come from? Integer constraint mainly come from the following. Integer constraint mainly come from which nodes should belong to this path, so 0 or 1. So we have much small number than the original mixed integer programming problems. Make sense? So it depends on whether the nodes in or not. Then I need to pick the control points inside this region. Each node is a convex set. And this continuity, there's certain points, control points, is on the common boundary or in the overlap region. So we have to force them to be equal, such that the trajectory is continuous. Yeah. So by picking these control points, picking the order and so on, I will guarantee certain differentiability and so on. So that's the idea. So we converting to become, we introduce more continuous variable, but I have much less integer variable. And a really good thing for this is you can just solve it, treat this binary variable as continuous, and basically you can get a lower bound, and this lower bound is very tight, which means you can using branch and bound in a very effective way to solving this mixed integer programming. So this turns out to be the case. Yeah, this turns out to be the case. So what we can do is, well, this is a bunch idea, and then I pick the control points, and we can get the continuous trajectory. Yeah. So the dots, the red dots is a continuous variable we need to pick. And this constraint come to this gx, right? And the total length is my ball. And whether this belongs to this is 0 or 1, right? So they belong to the path. Make sense to all? So this is the main idea. Yeah. So, but basically it's optimization problems. And then we can really apply to the problems, apply this idea, and we can really solve. And here is comparison. This blue line is what we showed before. This is based on traditional idea, mixed integer programming. And that's a number of the time steps, right? Horizon. And it's not a really fair comparison because we don't really do the sample. Yeah, we design continuous trajectory directly. So we compare is the number of control points. And here is a logarithm, so that's why it's almost flat, but basically it's polynomial. So it's much more scalable. So that's the hypothesis we proposed first, right? We don't believe the time horizon is the bottleneck. The what's the bottleneck? The bottleneck, actually, we found actually the bottleneck is the logic itself. Yeah, so I will show you some example. So this is another example. This basically is you eventually reach A, and you always avoid B, but meanwhile you reach C or D, right? Okay, C or D. So that's pretty much is your specification. And what we do is here is just to show we convert this into automata using some software. It takes several seconds. Then we construct the graph, construct the product, and that take some time. And this is simple enough. And the point is these two can be done offline. Yeah, you don't have to construct every time. You construct offline. When you construct offline, and will depends on your initial and target, then you just run the optimization. Yeah. So this optimization can run, but will take some time, but it's still much faster now. But this is another example, which is to make it more complicated. Is still the key and the door and the path. Eventually, it's we just make it larger. And you can see is this 32 minutes. This we believe this is the problems. This is the problem. This is 4 methods when you construct from LTL to automata. We call it bookie automata, but it doesn't matter. This is double exponential. It's double exponential. Double exponential respect to the length of the formula. Yeah. So this is not a huge formula, but it's already taken 32 minutes. Yeah. We can argue is we can do offline, but actually, if you're using better software. So, for example, we're using some commercial software, it can construct in less than 2 seconds. But still, this is still the inherent complexity, the logic itself. Yeah, which is reasonable, right? So if the logic is complicated, that's what we expect. But we do believe, but the complex optimization is pretty much let's say we take it. So, but the construction of this is actually you can see it's generated much more large, much more space. I think we can do better if we're using better software. So this is just to do it by the student actually. We just program simple C++ algorithm. So it's very straightforward construction. Yeah. So if you do like people do in the software engineering, we believe this can be really constructed very fast. Okay, then what we do is next is we try this idea to high degree freedom, to a higher degree of the configuration space. And this is just show you in the workspace, but we do planning in the configuration space. And the robot do is they just push the button and then go across the door. And this is narrow passenger problem. So we know it's difficult for the sampling-based approach. And for us is we can solve it pretty fast. Yeah. Because reason is this is very simple specification, right? Although it's high degree of the configuration space, but we still can solve it pretty fast. And another is we tried is even higher degree, 30-degree freedom. Well, here is just touching this box, right? Configuration. So we using inverse kinematics converting to the configuration space, and then we really using some existing approach to do the partition of the configuration space and construct actually, right? So there's a lot of techniques behind it. Another thing I want to say is here is you see it's try to balance, but actually we don't really consider the dynamics at all. Only kinematics. Only kinematic. We don't really consider any control, and we don't really consider about whether they can balance or not, right? It is more like the 4 robot arms. They're just floating around and try to. So we just try to show the scalability issue. And this is first part, and actually the lesson learned is well, so the complexity or the scalability we can really push. And the traditional approach, like mixed integer programming, although it's very general, but it's not inherent complexity, right? We can push it, we can really get them much more scalable. And it's polynomial in the number of control points, and we can do long time horizon. But still, the complexity is due to the task complexity itself. That's the inherent complexity. So we don't really do dynamics. So the next question we want to ask is, well, okay, if we consider dynamics, high degree dimension, high order systems, can we really be able to extend? Right? If, for example, the local motion is a very high degree, and the current approach is very difficult to guarantee stability. So can we do something? Yeah. So that's come to the next talk. Is can we? Yeah. The main idea is following: we're using reduced order model, but we don't want to using reduced order model in a just blindly. We want to in a principal way, in the sense. We want to guarantee something. That's my background. We always want to guarantee stability. So the idea is, I found it very interesting, but I want to share with you, but it's not a really perfect approach. The idea is following. The idea is using so there's some concepts called approximate simulation. Yeah, so actually we are just using one direction. So that's why the approximate simulation. What does that mean? That means we have some high order model, we have reduced model. And here is very simple illustration. And the principle is the following. I need to, if I have reduced model, I can design controller. I can get a trajectory. For example, I can guarantee stability, invariance, and so on. And I want to design, so it is design problem actually, it's control problems. But the design is I design the interface. The interface will take the x2, which is state from the reduced model. X1 is for the model, okay, thing. And we take the control U1, right? U2 is you using the reduced model design controller, which is usually simple to do. And what you want to design is you want to design U1. Okay, the output is U1. You want to design U1. So U1 is a control signal to your forward model. And you have two measurements, is Y1 and Y2, which is outputs. And approximation means you can have design such interface, or there exists such interface to guarantee if your initial condition is closed for the reduced model and your forward model, Y1, Y2, we say, then their trajectory remain closed, epsilon closed. Yeah. So why this is interesting? Well, there's one scenario we found is interesting. That's motivation for this work, basically. Well, we have certain stability condition for the leg locomotion. And we can convert transform these constraints into some center of mass of the robots. Okay. And we can approximate it. And we can using reducible model to control to make it invariant, right? So that's control the upper function, control invariance, and so on. So definitely, initially you are stable. And if we can control it using the approximation, if we can build a relationship with the forward model, if we can control this central mass, then in principle, we would be able to guarantee the stability. And the interface gives us the controller. Yeah, that's the idea. That's the idea, right? So we try this idea. And initially it's very interesting, right? That's promising. Yeah, that's some yeah, so we get this is push recovery. And this is just a standard 2P. Yeah, everybody know this. If you are working in this domain, you know this. And you just push it, and at a certain, it will not be a recover, but using our strategy, we'll be able to remain stability. Yeah, initially it's pretty promising. And we tried to the, okay, it doesn't work here. Let's just, hopefully works. Yeah, I think this. Oh, sorry, it doesn't show up. Well, now I skipped this. This is like a human robots, but I skipped, doesn't show up here. That's okay. I just want to, okay, maybe come to, well, this is interesting idea, but we found it's very conservative, basically. Another thing we are interested in is we want to push the limits, right? So what's when the review old model will fail? And we find it very interesting. So this is fun project, right? Side project is when we want to let the robots be able to recover and fall to the ground with 4 legs. Yeah, cat always can do it. It's amazing. And we find is all the reduced old model we can find is not be able to do this because when the robot is in the air, it has to change the angular momentum, right? Only thing can change the angular momentum has with the legs. But all the reduced old model, they will not be able to do it. Yeah, to simplify, for example, this leg is massless, so they cannot really change angular momentum of this. So that basically is okay, reduced old model. But still, I still like this approach, right? So I think it's still something we still can do. Maybe I could try some machine learning idea. Recently, I just got some idea. Maybe I can learn this interface instead of design, because when I design using the app function, so we find very conservative results. Yeah, it's almost not very useful. Yeah, that's motivated this the question: what's the limits of this real model? Well, then what we do is we just try this in our lab, and that's Wings actually. That's Wings. Handsome young man. He dropped the robots, and we add mass to the leg, and such that it will be able to change the momentum. And what we did is super simple. It's super simple. It's just optimal trajectory planning problems, and we run it open loop actually. And what we do is we just train it, solving this trajectory optimization and train neural network. Depends on different initial condition, then that's will give the control. That's a talk, right? For each joint. That's what we do. It's super simple. And as you can see, it works. It not always work, but definitely I just show you what is really working. But it's fun project. And why we show this is just we want to motivate our next question, right? So yeah, this is a fun project, and we find that this is actually we need okay. So I show you is the why we are interested in the third problem is due to form. So this is the project we show, and it's working, but you can see the video we cut exactly when the robot leg touching the ground. And the reason why we do that is because the following. Yeah. So when really make the contact is very highly unpredictable. Although initial position may be perfect, but when they really fall down, they fall. And that's why we put the math there. We don't want to break the robots. And the reason is the complexity is due to the contact. Yeah, that's another it's not just the order of this, right? So order of this degree freedom of the robots. And this contact makes this problem super interesting. Yeah, I know there's a lot of people interested in the contact-rich environments. When you do the robot grasping over the manipulation, this definitely you want to make contact. Yeah, so then we introduce some work that we try to solve these problems. We try to so this some initial work. This is early work, and again, this is just try some idea, and many is we try to understand the problems. And this problem we approach is just try to solving optimization, trajectory optimization problems. And we solve it pretty much we show here, the demo looks pretty impressive. But quite honestly, we assume we know everything. That's so far this talk. And we just run it, solving trajectory optimization using ILQR. And then we just apply to the robots. Pretty much we run open loop in this sense. Yeah. So it takes a lot of time to compute the trajectory. It make contact, and the reason why we can make contact, because we using some type of elastic contact model that we can predict what's the contact force. So that's the idea. The main thing is we convert into some optimization, trajectory optimization. And it's too slow. Basically, it's too slow. So that's motivated us to consider a different approach. The idea is based on the inverse dynamics, and it's super simple idea. So again, in this talk, we assume we know everything. We don't consider uncertainty at all. So here is optimization is using inverse dynamics, and we optimize with respect to Q directly. The Q is configuration. So we know the Q, we know Q dot, we know Q double dot. So we can, using inverse dynamics, we will be able to compute the top, right? The top. And also, the Q not only include robot joints, but also include the objects I'm going to manipulate. So which means I know everything. So based on that, I would be able to predict whether I make contact or not make contact. And I can get the contact force, Jacobian, and can into the dynamics. This inverse dynamics replaced in the top sheet. So as you can see, this become a long is optimization problem, basically, right? For every time t, and we have some reference and so on. So that's become unconstrained optimization. And we did add a constraint. Yeah, why we added this constraint? So the reason why we added this constraint because the object is not accurate. So the robot cannot really, we cannot, unless I touch it, otherwise it's not problem. So this is, if I don't add this constraint, I can see some magic happen. You see the ball, I try to using these two links, simple robots, to rotate the ball. Yeah, I know the configuration Q1, Q2 of the robots, but also I know the just 1 degree freedom now of the ball, right? I just rotate the ball. So if I run the optimization problems, is just toy example, but we see some magic happen before the robot arm touch the ball, the ball start rotating, which is not reasonable. Yeah, so we have to add a constraint. So what we do is we add constraints such that before you touch, actually depends on the Q, then this no torque, right? It cannot move itself. Then it becomes more reasonable. Yeah, it's become more reasonable. But then this becomes constrained optimization problems. Yeah, so the major efforts for my students is just to solve it fast. You know, spend a lot of time on that. Yeah, so that's a main idea actually. That's a main idea. And once we get a solver, actually, then we try to push to more interesting scenario, and this is Hopper. And the interesting thing is we just given you a target, and give you just some trajectory we want to forward, right? So forward. Want the robot to go forward. It's not based on reinforcement learning. It's based on optimization. And the robot basically figure out when it make contact, when it break contact, and make the move. All through is optimization. So that's interesting. Another interesting thing is this is the same thing. We don't really design the gates. The gates emerge in itself. Yeah. So that's basically is this approach is about. So we convert into optimization problems. And this is a push and make contact, break contact, and so on. So again, this everything behavioral emerge through the solution of this optimization problem. And this example is interesting. You have this finger robots, right, to rotate the ball. And the interesting thing is this gaze, this kind of pattern of the moving of these three fingers is automatically emerged from this optimization. We make contact, break contact, and the velocity and so on. So that's interesting. Yeah, so and we do is upside down, and we argue this is difficult for reinforcement learning or learning-based approach. So you really need a very good starting point, right? So otherwise you drop the ball, so that's not really feasible. we would be able to do that based on optimization, and we pretty good. And this is a constraint, and we find it's pretty close to zero. It's supposed to be zero, but not perfect, right? So it's pretty close. So we think is interesting. But to be fair, this is difficult for learning problem. But a learning problem learn a policy. But for us, we learn a trajectory. So that means we learn Q0 to QF, basically. Yeah, so we learn one trajectory. So in that sense, we can learn fast. Yeah, so this is not a real fair competition. I don't claim that's better than reinforcement. No, that's not my claim. But we are learning different things. Reinforcement learning, learn a policy, so different initial condition, you still can get a trajectory, right? So that's not exactly what we are doing. And there's some recent efforts. Recent efforts is we try to close the loop. Yeah. So all we did so far is we solve optimization, and we try to solve it fast and apply online. And it's fast to a level that we believe we can do online. Yeah. So online is very simple. It's just similar to model predictive control. Yeah, that's a very simple control approach. And the interesting thing is, if we do open loop, like we did trajectory optimization, then apply to robots. And we have the same task, just rotate it 90 degrees. If we don't run open loop, you can see this robot just push it and leave, let it rotate. And interesting, if you close the loop, some emerging behavioral interesting pattern is the robot arm push it. Initially, let's say repeat, let's push it. And then they try to stop it, right? Add some friction, try to stop it. And that's very interesting. So all this is, we don't tell the robots how to do. There's no demo either. The robot is optimization engine finding this behavior. Yeah, which I find is very interesting. Yeah, so we are this is ongoing now. I think we are just choosing. Another thing is we don't have any uncertainty. So another very interesting question for us is, what if we include the uncertainty? What if we don't know exactly the configuration? What we can do, right? So which means we feedback the loop, not just using model predictive control. We feedback using some vision, for example, right? So we have certain uncertainty. How can we do it? Yeah, I think this definitely I need a brilliant students that we will carry on this. Yes, it's interesting research direction. So we still have some time. I don't want to take too long because I know everybody is busy. I still have several slides, but I try to open a little bit discussion. Well, my background is control, and I have a lot of interest in the robotics, especially autonomous robots. And this is just some history we share. The reason why we look at the history is we can see a little bit of the future. I think the future is see this scalability, high degree freedom, and uncertainty, autonomy. I think that's the main trend still, is my belief. But if we want to make it working, I think we have the physical dynamic control, we have the perception, we have human robot collaboration, we have the motion planning, task planning, and also above that, we have knowledge base, we have AI systems, we have the cloud. I think we need everything to make it work. But unfortunately, that's the comments I want to make is, unfortunately, we don't really, or we have too fine division between departments. We have mechanical engineering, we have electrical engineering, we have computer science, and we educate our students in a quite different skill sets. Yeah, we seldomly have prepare our students for future talents that would be able to do all. Yeah, so that's something I think is something we should correct. That's my feeling. Because when I offer the class, one comment is I taught perception class because when I want to learn something, I offer new class. Although I don't know much about before, but I bravely volunteer to teach, and I learn a lot. But feedback is, well, this is 2CS class. Students are afraid they don't want to be able to get A in the class, so they reluctant to take the class. Yeah, which I think is a little bit, we kind of need to overcome this barrier. Yeah, so we want to encourage students, or maybe encourage a certain education system, curriculum, such that we will be broader. Yeah, because I think all the interesting questions happens at the interface. Yeah, so if you just focus on dynamic control, which is great, but you can borrow a lot of things from other domains, right? So we got all the, I think the fundamental challenge still is almost the same. Scalability uncertainty. That's the signal size. Well, for the autonomy, for the robots, I draw three, but many two, but I draw three. So one is the scalability, that's something we talked today. Another is uncertainty, that's the axis. Another is we call complexity, but complexity, scalability is have a lot over them. Yeah. I draw three because that's the maximum I can draw. That's it. Yeah. So we see scalability, we see we saw the scalability due to the task complexity. We see the scalability due to the high degree freedom. And there's another scalability, it's just a number, right? So multi-agent system, large number, swarm, robot, and so on. And we see uncertainty, but today we don't talk about uncertainty at all. What I want to argue is autonomous driving is difficult. The reason is very uncertain. But even more uncertain is some rescue tasks. Yeah, so the service robots is hard because it's very unpredictable. So that's something I think is just motivate my research. Eventually, I hope my career, I can reach some point there. I can develop some fundamental approach, make some breakthrough for the scalability uncertainty, and we will be able to handle it, right? So yeah, so some people ask me what's my research interest. I think I'm not really stick to particular platform or particular approach. I think this is driven force behind my research. I really want to make some fundamental contribution to each axis, such that bring to some systematic approach that I can. And nowadays AI is a powerful tool, right? That enable us to do something, solve some problem at a scale that we cannot solve before, handle some uncertainty that we cannot handle before. Yeah. So we have to pay attention to the AI developments. I think that's the last slide. Thanks to my students. Many are former students now. And this is a group, robotic control group at Notre Dame. And this is during the fall, which is the most beautiful season. And the football season, that's my favorite part. Okay, so welcome to visit Notre Dame. If you have a chance, let me know. I'd like to show you around. Okay, so that's all. Thank you very much.
Okay, any questions for Professor Hanley? Yes. Yeah, go ahead.
Thank you for a great talk, and I actually thank you for all the work you have done because I'm using one of your library ST5 for my research. Yeah, and you mentioned about the complexity and the length of the temporal specification is one of the reasons making the station longer. So I wonder if there is a pattern or the structure that is preferable for the computation. So for instance, we can write always as using the eventually, or we might write very like a long depth specification, like eventually of always or eventually of until something like in a more simpler way, but a longer way. So is there any kind of preferable patterns that make the computation faster?
Well, definitely. I think it's how you write this formula definitely make a difference. I totally agree. And there's some standard forms in the formal methods, and a lot of algorithm depends on the standard form. Yeah, so I think I don't have general answer to you. I think it's a lot of time we prove is based on this class standard form, right? So we prove the complexity and so on. But for the particular problem we're working on, if you have some way to simplify the problems, simplify the specification, definitely the shorter the better. Because this number of integer variable and so on introduced totally depends on, for example, if you convert into a automata, so the states will depend on how many subformula you have. It's a power set of subformulas. So if you can simplify the formula, definitely it will dramatically improve your algorithm efficiency. Yeah. So I don't think there's a general solution. How we do that, that's the best way. I think that will be depends on your problem. Thank you.
You're comparing like the MPC versus reinforcement learning, like how you're able to get to the solution that was better than what reinforcement learning.
No, that's not my claim. I don't claim this is better than reinforcement learning. I just say, okay, this is hard problem for reinforcement learning, and we can using optimization problem to train. No, not to train, to really find the control actually. We can do it, but this is not comparable with reinforcement learning, because reinforcement learning learn a policy. And here we just learn a trajectory. So I'm not claiming this is better. That's not my claim. I think it's interesting thing is, I think interesting question we could ask is, what we can do if we find one trajectory, can we do better with reinforcement learning? For example, we can using warm start, right? So using this as more like inverse reinforcement learning, and to find the policy. Maybe that's a better way that we can combine. I don't claim this is not really to compete with reinforcement learning. This is more like alternative approach that solve problems that could be difficult for reinforcement learning. And we learn something, and we learn this could help reinforcement learning to address this difficult to warm start, for example. Right. So you inverse using reinforcement learning, using inverse, and you would be able to maybe you can find the policy. Right. So then you don't have to start randomly. You can start with some pretty good policy, and you try to do reinforcement learning to make it better. Maybe that's a better way. Yeah. Sorry, I gave wrong impression. I'm not claiming this is better. That's different, just different approach. And the take-home message is optimization is a pretty well-developed domain. So we can take advantage of optimization, a lot of structure in the optimization problems. So we can take advantage of optimization problems and make the problem more scalable, make the solution more scalable. Yeah, for example, machine learning, we know this is heavily based on optimization. Yeah. Thank you.
Very nice presentation. Thank you. My question was related to your temporal logic. So
Okay.
once we have a temporal logic, based on your algorithm, we can find a fast online solution. But if I'm understanding it correctly, for task allocation problems, the problem is making that temporal logic.
Oh, that's different problem.
Okay.
For us, it's given topologic. Yeah, so I plan the trajectory in the configuration space, certify the state equation. So the task allocation problem is different. Task allocation problem is to allocate this task to each agent, right?
Yeah.
Yeah. So and I have another student that work on very interesting is not task allocation, it's task decomposition problems. So basically, I have a team of robots, I have a team task, and then based on the capability and the resource, I decompose. In the sense is in the logic sense. In the logic sense, I divide the formula into subformula such that the robots, if they achieve the subformula, they can achieve the big formula, which turned out to be very hard problem. That's related to the task allocation. Task allocation, if you already decompose it, which you should to assign. Yeah, so that's not the problem we solve here. Yeah. Thank you.
Thank you for your very nice talk. My question is regarding your simulation function.
Simulation function,
Yeah. So if I understood correctly, the interface function requires the state of the full order model, right?
You mean here?
Yes.
Yes, you need a state model, yes.
So does that mean that the full order model needs to run in parallel with the reduced order model?
Okay, so two ways you can think about it. So yes, in the interface design, in this form, yes, you need a state from the simplified model and a state from the full order model, and the control from your simplified model, which you design. And the interface give you the controller and to control the full order model. You can think about the interface plus the simplified model is your controller. Make sense? This is a controller. This is more like feedback controller, right? Yeah, so because it's much easier for you to design the U2 to satisfy certain specification. Like we showed, like if you control the center mass within certain range, that's control the upper function. You can construct a much lower, usually it's much lower dimension. If you design it, control it, and this signal U2 is available, and your X2 is available, it's in your computer actually. So difficulty is to get X1. Let's assume you have X1. Then you automatically get a U1 by design the interface. But the design the interface is non-trivial. It's almost as hard as design nonlinear controller. So we're using control function to design it, find to be very conservative. Yeah, that's the result we didn't show here. But this is interesting principle. That's something I feel love actually. I think we have some new idea. Maybe we should try. And but yes, we need a control. We need a X1, X2, and a U2. You know.
And this does not consider any disturbance that acts on the full model.
No, we don't consider any disturbance. That can be extended. Yeah. If you have robust control function, for example, you would be able to. Yeah. So I think this is just this is not all work. This is 2909. There's other people work. This is from formal methods domain. So our motivation for that is we are working together with some people working on Lego robots. And we found the most difficult problem for them is to guarantee stability. They are using model predictive control. And they are using reduced auto model. So we say, okay, so can we guarantee stability by using reduced auto model? And that's bring up this idea actually. Yeah. So yeah. So we don't fully extend this approach, and we just found this is elegant from the principal idea perspective, but so far we didn't really successfully implement it. We just run some simulation and find at the very beginning very promising, but we quickly hit. I think we're using design the interfaces almost as hard as design the nonlinear controller. Is no much benefits. Yes.
So just a follow-up question. I'm curious about how do we get the full model here? Is it being learned or is it?
For the model, you can using Euler Lagrangian or Newton Euler iterative approach. That's usually assume is given. Is well understood in the robotics. Yeah, is you have textbook. I think this is for the model. I think Dr. Hu is working on the model, right? So that's my understanding. I'm not a really robotic guy, but my understanding is this is well understood. You kind of, but the reason why people don't use it or it is high order, and you need a lot of computation to do that. And because of very high order, usually 30 degree, 70 degree, for example, then it's very difficult to control. Very difficult for you to design and control it. Yeah.
So is that you are from our expert knowledge?
Yes. Yeah. We assume this for the model is given. Yes. Yes. Usually in the literature, people just using simplified model to do the model predictive control, but there's no guarantee at all. So we try to bring the bridge between this, right? When you're using for the model, we say, okay, using simplified model, but you still have confidence. Yeah, that's a main motivation for us. We do that. Yeah. Yes.
Hi, Billy. Thanks again for your great talks, and I hope you found like your motivation on scalability and uncertainty very inspiring. I wonder if you would like to give a very high level overview on how uncertainty is handled and how is that combined with scalability problem, how these two domains overlap.
Well, that's big question. So
Very high level, sorry.
well, so principle is yeah, that's great actually. So the uncertainty is everywhere. So I educating control. So we can see a clear thread in control literature to deal with uncertainty. So classical control, we have frequency domain, body plots, and so on. We always do the phase margin, gain margin. That's robustness, right? Let's deal with uncertainty. And then when we extend to the multivariable system, multi-output system, we find it's difficult. So that's come to the Pontryagin, LQR, LQG time programming, optimum control. And people quickly find is the optimum control is not robust. Yeah, LQG is very, very fragile. If you change a certain parameter of your state variable status transition matrix is go unstable. So then that come back to the frequency domain, introduce the robust control and adaptive control, learning-based control. You can see a clear thread of uncertainty. But I want to argue is, although we have very mature control, and it's very interesting, very complicated, but we only deal with local uncertainty. In the sense is we control loop, and we deal with disturbance, deal with the noise, deal with parameter uncertainty, adaptive control. So that's still local. And if we push for the next generation of intelligence, robotics, for example, intelligent robots, the uncertainty is everywhere. So this uncertainty, for example, from driving, it's not just the control your engine, your stability. It's other behavioral of other drivers, for example, road condition, for example. traffic light, for example, pedestrian, for example, that's come from environment. That's very difficult for control. Yeah. So then another is for scalability. Another is because my interest is very interesting. I educate in hybrid systems, so I'm interested in the formal logic as well. So that's why when I was in Singapore, I started pretty much focus a lot of efforts on the formal logic. I'm very interested, still very interested in. And the reason is I found the formal logic, you can see a clear trend in the formal logic literature to deal with scalability. They have a lot of very good ideas, symbolic approach, abstraction approach, by simulation approach. So, but until very recently, I mean, 10 years, they started working on uncertainty. But for methods and control, in my opinion, they are pretty trying to address the same problems. Yeah, so it's just different dynamic. One is logic driven, another is physical driven. And for methods deal with verification for model checking, right, for example, and a synthesis problem. But for control is analysis and control. But they never barely they crosstalk. What I want to say is this scalability and uncertainty are very fundamental challenge for almost all engineering problems we're facing today. And to really handle it, I think it's difficult to really. So back to you say, okay, so I just back to my personal research interest. I found is we are in the AI machine learning era, and the machine learning literature gives a lot of very powerful tools. But we cannot beat just we cannot expect the tools developed by AI domain, AI computer vision, machine learning people that we can plug and play to the problem we are facing. No, that's not going to work this way. The computer vision people, they are developed this follow their own agenda. They are interested in classification problems, segmentation problems, semantic problems. They are not exactly the control problem. They don't really care much about the dynamics, physics, and so on. But on the other hand, okay, so this is a tool we can use, but we cannot just using it blindly. I think we have to understand it. And we use it in a principal way. Like, for example, this is one principal way that I would prefer. So give an example. We have a lot of uncertainty. So if you go to computer science people, inverted pendulum, they just using they call end-to-end training, right? They just push a lot of data and train and get a controller. But why not just using the physics? Inverted pendulum, we know the physics. Yeah, we know the energy function, we know Hamiltonian, we know all the Lagrangian. Why not using this? Because energy, dispatch, energy, invariance, all these principles should hold. They're physical systems. So there are a lot of these principles and also a lot of structured problems. When we design the controller, we know the controller, we kind of have observer and the controller itself, right? So we have stability, and we can design in such a way. So we have structure, all problems. So that, in my opinion, that'll help a lot. And we can do something, actually, this is a tool, and I would say we should use it, but we shouldn't use it just blindly. We don't expect they prepare the tool for us. This is something we can develop as well, and develop to solve all problems. I think that's an opportunity. That's opportunity. And we're developing very fast. Okay.
Good question. Yeah, go ahead. Yeah.
When you apply the logic method for planning for applying your space of lots, so the reason you mentioned why we did not include dynamics in the constraint is because if it's making the logic too complicated. Is that the only limitation here?
Well, it's just too complicated. Yeah. So what we hope is, for example, here, if we design this, for example, this red is from configuration space, then we just design to track it. That's the idea. We use a hierarchy control. If we design using the forward model, that control dynamics, design it, that's just it will be hybrid system actually. That's become hybrid optical control. Yeah, hybrid optical control is very hard. Yeah, it's very hard. We can get some Pontryagin condition, and even without the hybrid mode switching, solving the Pontryagin, the split boundary problem is not easy, right? So we have a lot of efforts to do. And that's just the reason why we don't do. Simple answer is we don't know how to do it yet. Okay.
Yeah, I have a question.
Yes.
So we can do trajectory optimization and also central logic to plan tasks. And I'm curious about what are your thoughts about combining this with reactive planning? For example, basketball is flying to the robot and
Yeah.
quickly dodge the ball. So what are your take on combining this with focus?
Yeah, that's another area I'm very interested in. Active, reactive planning or active perception. Yeah, okay. So that one is ongoing research. So the idea for us, we try to push or pursue is we put everything into the Bayesian framework because the perception is influence problems. And we can pose a control problem, any problem, as influence problem as well. So we don't think it's as deterministic. We think everything is probability. So the probability, what does that probability mean? Control. Well, that means you have policy in your control domain. That's a functional space. And then you have distribution in this policy domain, and then you want to maximize the probability, which is optimal policy. So that's giving you that's convert the problem of control problem become influence problem. I think the reason why I'm interested in this idea, because that will make the perception and the control problems in a unified framework. And we can use machine learning tools to learn. They are not necessarily to be data driven. Not just to say, okay, we build the data to drive it. And we have a lot of principal way to train for them, for various inference. So that's again converting to optimization problem. So it's in principle, it will unify the framework.
Yeah, that sounds super exciting. So hopefully maybe next time you're here.
Hopefully I can get some results. Yeah.
Right, yeah. Let's thank Dr.
Thank you. Thank you for your time.